Okay.
Assalamu alaikum warahmatullahi wabarakatuh. This is our project about ball balancing system. And the group members are Abdullah Al-Qahtani, Mish'al Al-Shamikh, Muhammad Al-Nakhli. Introduction. The objective of our project is about to design and implement a control system of one-dimensional ball balancing system to stabilize the ball by controlling the beam angle. The system's components are the beam and the ball and the sensors and the actuators. The beam consists of two rectangles of 27 centimeters and width of 4 centimeters each. And the ball is with the radius of 3 centimeters. And the sensors are, we are using an ultrasonic sensor in one of the ends. And the actuators motorize the mechanism of to tilt the beam. The project process consists of 4 main steps. We start with fabrication and sizing, and then the assembly of the components, and then programming and control implementation, and then the mathematical model analysis. Fabrication and sizing. This stage involves precise cutting and sizing of all components required for the system, ensuring accuracy and compatibility. We have one beam of length 27 centimeters and width of 4 centimeters of each rectangle, and the base of the rectangle is with length of 31 centimeters and width of 8 centimeters. And we have two trapezoids with top width of 5 centimeters and height of 10 centimeters, and the base width of 15.5 centimeters. And the second stage is the assembly of components. In this phase, the individual elements were assembled to construct the foundation of the structure of the project. First, we mount the beam on top of the trapezoids, as you see here in the video, and then we position the trapezoids on top of the base, and then we add a rotation by placing a straw beneath the beam to have the rotational movement. Or we install the ultrasonic at the end of the beam to detect the distance of the ball. And then we add the control mechanism here, and then we integrate Arduino in the outside. It should be placed here in the final stage. Now we go with Michel.
Hello everyone. Now let's start with the programming and control implementation. First, we have to get the theoretical data, and we use MATLAB to give us the code, to give us the desired parameters of the PID controllers, and it shows us the step response with the automatically tuned PID controller, and these are the value that we are given, the KP and the KI and the KT. And this is the graph of the Rot locus of this controller. And we know that if the system is on the y-axis is not stable, but the step response shows it's stable. So when you zoom in the Rot locus graph, you can see it's not in the 0 exactly. It's left of the 0 by millimeters. The next slide, and this is the Rot locus of the system after we give the desired parameters. Muhammad Al-Nakhli will talk about them, which is the rising time and the overshoot. And we can see here the closed loop step response of the PID is much better. And after we implement a lead compensator, we can see that we know that the lead compensator shift the Rot locus to the left side to give us more range and stabilize the system much better. And we also ask the MATLAB to give us the damping ratio zeta and the natural frequency omega n. And because since our system, when we find the transfer function, which was second order system. So we know how to calculate the parameters from the equations that we took before. And now for further details in the mathematical models, Abdel will talk about them. Abdullah.
Okay.
Now we'll continue the programming part, but after this slide, the Hamid al-Nakhli part. Here you can see the programming using Arduino app, which is and the KP, KI, KD that we found them, and we can notice that the PID parameters is not matched with the theoretical data due to various of reasons, such as the resistance, the friction, and the resistance of the wire that do not allow the beam to move freely. And for example, you can also say because the connection of the wires was not installed perfectly because of some wires, I installed them by cutting them and wrap them around the other wires. So there might be a loss of power. And this was the code. And now Mohammed Nakhli will talk about the mathematical model.
Okay. Before we'll speak about the mathematical model, I want to say that here in our model, we forget we didn't care about the slipping and the friction between the beam and the ball, so it was negligible. So as this difference, it will make some difference, of course, in the result at the end. Before, I want to speak about the design criteria, which was the rise time to be 0.205 second, and also the settling time was 1.91 second, and the overshoot was less than 10.4 percentage. Okay, about the mass, we calculated and we found that the mass of the ball, it will be 0.002 kilogram, and also the radius was 30 centimeter. Sorry, 3 centimeter, and the lever arm offset was 10 centimeter, and of course gravitational acceleration was 9.8, and the length was 0.27, and the J, which is mean the moment of the ball, was 9.9 multiplied by 10 أس 10 سالب 6. Okay, let's go to the next slide. Here we found the mathematical, the system parameters, which is we use it, and we will use it. So in the next slide, which we use it for transfer functions. Let's go to the next slide to see it. Okay, here we'll see that J over R square plus M multiplied by R derivative, it will be equal something. Here in the transfer functions, we'll use Laplace transform to simplify as what we learn in the lectures, simplify the equations, and after that we get that the transfer function of the ball, it will be mgd over L multiplied by J over R square plus M all multiplied by S square. Okay, or 1 over S square. And we use MATLAB to find the result of that. So we find the result of the transform, the transform, it will be negative 0.55 for 1 for 2. And this negative, it came because of the negative from the gravity acceleration. And for the next slide, we find the state space to know what is the K and KP and what should we use for K. So we use it as what we learn in the end of the semester, and we find that A, it will be equal as this matrix, which is, you'll see it here, and also the B and C and D. And this is the end of the equations and mathematical modeling and analysis. So now we'll show you how was the circuit.
Okay, thank you, Mohammed. Now this is the picture of the connection of the project. Here on the left is the connection, but we have a little difference. We didn't use Arduino Uno, we used Arduino Mega. And due to the reason that we don't have two port of the power source, I use the breadboard. So I connect the power source on the power system, the powering of the breadboard, and connect both the sensor and the servo motor. And that achieved our purpose. So we achieved the goal. And the next slide, Abdullah. Here in this video, we can see that we video our system, and it shows the connection and the code and the value of the PID parameters. And now when we lift the ball to the right, we can see it, how it achieved the desired distance between the sensor and the ball, and it will balance in the middle. And also we can add a note, but I will add the note after the second video. This is the second video when we move it to the left. So we covered all the cases which may cause some instability, but it didn't. So we can visualize that tuning the system by experimental is much better than theoretical, because the experimental parameters of the PID are different from the theoretical, and it achieved our purpose of this presentation. So we can notice that the changing of the KP will make us isolate to achieve the desired position, and changing the KD will make us stop at that position, not isolate on it. And the KI is just accumulating the error so that it goes back to the desired position. So in the conclusion of this project, a report was designed and implemented to balance a ball on a beam using PID controller. The system allowed rapid tuning of PID parameters, enabling dynamic adjustments to improve performance. And although theoretical predictions were initially made using MATLAB simulations, the result of the physical experiment deviated from expectations due to real-world factors such as sensor noises and system delays, and the frictions, and some factors that we neglect them since they do not affect the system that much. And during tuning, it was observed that manual adjustments the PID parameters based on visual feedback provided better results than theoretical values derived from MATLAB. This underscores the importance of addressing the gap between theoretical models and real-world implementations. And we can improve in the future to further enhance our system, including incorporating a digital filter for ultrasonic sensor to reduce noises and improved accuracy in the position measurements. Because in the measurements, I took the reading of the sensor and I placed my hands where I want the system to stop, but there is some error because my hand is not flat. so there might be a possibility of error. Additionally, replacing the Arduino Mega microcontroller with the Raspberry Pi would provide greater processing power and flexibility. The Raspberry Pi could handle real-time data acquisition, processing, and live plotting without being limited by the constraints of the serial communication buffer. This will enable the controller to operate